Okay, so this is the outline of chapter 33 about the electromagnetic wave. 电磁波. Okay, so in the outlines, of course, we will introduce what is the electromagnetic wave, and then the energy transport and the Poynting vector. Okay, and then we will also introduce the radiation pressure. Okay, so this is like the characteristic of a particle. Okay, particle. Okay, of course, this is a wave. Okay, and then in high school, probably you have learned a term called 波粒二象性. Okay, duality. Okay, so it also tells you that the EM wave is of course a wave, has the property of a wave, but also it has the property of the particle. Okay, so we'll introduce those properties, and then we'll introduce an interesting phenomenon called the polarization. And then this part is probably you have learned it in high school, the optic, about the reflection, refraction, 反射折射, and then total internal reflection, 全反射, and then polarization by reflection. Okay, so this is about the Brewster angle. Okay, so okay, so this is the page 0. Yeah, so what is electromagnetic wave? Okay, so we start from the Bible, not from the physics. So yeah, actually, Genesis. What is Genesis? 创世纪. Okay, so if you are a Christian, you know what is the Bible. Okay, 创世纪. Okay. Okay, so actually in Genesis, first chapter, first to third. Okay, this is the NIV, New International Version. Okay, so actually it is like I can only remember it in Cantonese, so it should be like 起初神創造天地，地是空虛混沌，淵面黑暗，神的靈運行在水面上，神說要有光就有了光。Okay, actually I cannot remember in Chinese, so so that is the idea. Okay, so it says in the beginning, God created the heaven and the earth. Okay, of course in the Christian they consider like God created the world. So the God created the world for several steps. The first step is to say, okay, there should be some light, and then there's light. So in the first day, the God created light, and then the second, third, until the sixth day, okay, he created all the things in the world, and then for the seventh day, he take the rest. That's why every week we have 7 days. Okay, okay. So this is not physics. This is theology. 神學. Okay, so going back to physics. Okay, so we see this Maxwell rainbow again. Okay, so actually I've mentioned it before. So when you look at this so-called spectrum, 频谱怎么写？频谱 okay, 频谱. Okay, so yeah, we have 2 axes. Okay, one is the wavelength, and then one is the frequency. Of course, they are inversely proportional to each other. Okay, the relationship is like F equals F lambda. Okay, frequency is F, wavelength is lambda. Okay, F times lambda. Okay, and then equals a constant C. C, this is the speed of light. Speed of light in a certain material, but usually we'll mention it in the vacuum. 真空的 vacuum. Okay, so And actually, if the frequency is higher, we'll say the energy of a photon is larger. Okay, so the equation is like E equals hf. E equals hf. So this is the energy of a photon. This is the Planck constant. This is the frequency of the EM wave or the wave. Okay, so yeah, in this spectrum from low frequency, we have long wave. Here we have a radio wave. Okay, to propagate for the radio signal or the TV signal, and then a little bit higher, it will be something like for the mobile communication, Wi-Fi, or whatever. And then even higher, maybe 5G or whatever. And then up to this part, it is infrared light, infrared, which means 红外线. And then here is the visible light. So probably when we consider rainbow for a primary student, you consider, oh, this is the rainbow. But actually, if we mention the Maxwell's rainbow, it not only consists of the original rainbow, but it extends quite a lot. Okay, this rainbow only occupy a small portion. Okay, from 10 to the 14 hertz to not more than 10 to the 15 hertz. Okay, so this is a very narrow region. Okay, of course this scale is in log scale. Log scale means every step is 10 times larger than the previous one. Okay, so this is like a log scale. SCA, log scale. Okay, so here after the visible light, we have the ultraviolet, 紫外线, and then we have X-ray, and then also the gamma ray. Okay, so these are the high energy particle. And of course, as F and lambda are inversely proportional. If the energy is high or if the frequency is higher, then the wavelength is shorter. Okay, so that's why if we have a radio, okay, when I was in primary school, then probably a radio is like this. A radio have a very long antenna. This antenna can be like 1 meter or at least several tens of centimeter long. Okay, so to really receive the frequency around 100 megahertz, and then even if you would like to use your mobile phone to listen to the radio station, not from the internet. Okay, if you really want to listen the radio from your using a mobile phone from the FM signal, you probably need to connect a earphone, okay, with a line. Of course, it can be a Bluetooth earphone. Otherwise, because the earphone with the line act like the antenna, 就像跟天线那样. Okay, so and for the radio, the frequency is lower, so the lambda is larger. So you can imagine the antenna should be longer. But for Wi-Fi signal, the frequency is like 20 times higher. So actually, the dimension of the antenna is much smaller. Okay, so in Maxwell time, the mid 80s, around 1855. Okay, so he actually unified the Maxwell equation, and then based on the Maxwell equation, he really solved the solution for the wave equation. Okay, he can use the Maxwell equation to derive the wave equation, and then by solving the wave equation, he really found there should be something called electromagnetic wave in the world. Okay, so yeah, so actually he only found it in a theoretical way. He didn't do any experiment to really verify the result. Okay, so until almost like end of the 19th century or at the beginning of the 20th century, okay, Hertz discovered the radio wave. Okay, so that's why the frequency the SI unit for the frequency using Hertz Hz is the short form for this HERS. It can be HE. Okay, it can be HE. Okay, so the Hertz is Hz. Okay, discover what we now call radio wave and verify that the same speed as visible light. Okay, so we now know a wide spectrum, okay, called the Maxwell rainbow. Okay, so what? Okay, so here. Okay, so this is the setup to generate some EM wave, Okay, so this is the energy source. You can consider it's like like a battery or whatever. Okay, to generate a sine wave, probably a sine wave. And then here we have a RLC circuit. Okay, so in chapter 31 we already know this is a RLC circuit. If we provide a sinusoidal, and then the output should also be a sinusoidal. And then of course the oscillating frequency. The oscillating frequency is at 1 over square root of LC. Okay, so if you also provide this frequency, then the output here will be maximized. Okay, and then here is a transformer. Here is a transformer, so that the energy oscillating here can be transferred to the next stage. Okay, and then here we have a next stage, and then connect to this one. This is called electric dipole antenna. So this is actually an antenna, 天线. Okay, transmission line. Okay, so Okay, so this is too difficult to explain. Okay, so just consider it's just a line. Okay, and then it can be connected to the antenna. Okay, of course it can be a dipole or in any shape. Of course, in your mobile phone, the antenna is not like a dipole. It should be like it should be something like this. It should be something like this. Something like this, or something like this. Okay. So so actually it's just like a coil. Okay. And then of course it's difficult to mention or why it will be like that, or what is the relationship between the shape and the pattern of the EM wave. But here it just mentioned is it's just a dipole, so it will transmit something called the EM wave out. Okay, of course it is just like a source, so you just like you go to the lake and then you throw a stone in the lake, and then the suppose it's a lake, and then you throw a stone in the lake, then there will be some wave propagating to different direction, like this. So actually you consider this is a source, so it will be the center of a sphere, and then the EM wave will propagate in a spherical shape, 就是球形的往外去传播 propagating. Okay, so this is the traveling wave, and this line we call it the wavefront. Wavefront 叫做坡前 wavefront. Okay, so you consider at a certain moment it propagate to here, and then for the next step, okay, after let's say delta t later, okay, the wave propagate to here, and then also delta t later, and then this wave propagate to here, and of course later on it's still generating the EM wave, okay, at each moment. So it is just like the wave is propagating outside. Okay, you can feel that this raven is moving in like a spherical, like the concentric spherical. Yeah, just you can imagine. Because the EM wave cannot be seen by our eyes, so you can imagine if you throw a stone in the lake, and then there will be some wave propagating to propagating to different direction, propagating to outside, and then there'll be more and more rings. Okay, so yeah, of course it is a spherical shape, but it will be difficult to describe using an equation. Okay, so here we'll consider P is a distant point at which the detector can monitor the wave traveling past it. Okay, we will assume that this P is far away from there. Okay, so even though it is a sphere, if it is very far away, let's say it has a very large owl. Okay, so if the owl is very large, then if you just cut this part out, you can consider it is just a plane. Okay, it will be just a plane. So you can also consider it as a far field, just as what we have mentioned in chapter 22-23 when we consider the dipole will generate some E field. Okay, we'll consider if the distance is far away, much larger than the antenna. Okay, here we also consider, let's say if it is L. Okay, if L is much larger than L, then we'll consider it's a planar wave, planar wave, or plane wave, or plane wave. In Chinese, it is called a 平面波. Okay, so actually it will generate some E field and B field. Okay, so actually in the textbook or in this slide, it will just tell you the answer. It will not tell you why it will be like that. So after that, I will have a supplementary note to tell you why or how to really derive the wave equation using the Maxwell equation, the differential form of the wave equation. And then by solving the wave equation, we can verify many equations occur here, like 33.1, 33.2, 33.3, so on and so forth. Okay, 33.5. Okay, by solving the wave equation, we can I can tell you that why it is correct. So for the slide, you just assume that it is correct. Okay, and then just listen to what it really telling you. Okay, so actually, it said that based on the observation. Okay, so yeah, so we'll observe that actually at point P, it can really observe that the E field and B field is actually varying. Okay, so at the first moment, E field and B field are maximized in one direction. Okay, so the E field pointing upward and the B field is pointing to the left side with the greatest magnitude. Okay, 最大的振幅. Okay, and then later the E field and B field reduce the magnitude, and then until this point reduce to 0, and then later pointing to the other side, okay, become larger, and then up to this point, okay, greatest magnitude again, but point to the opposite direction, and then become smaller 0 and then point to the original direction and then going back to this one. Okay, so it's just like also like oscillating. Okay, but there are some property here. Okay, so here it tells you that, oh, here we can find out that there are 4 properties. Okay, the first one is the electric and magnetic field, E field, B field, are always perpendicular to each other. Perpendicular to each other, and not perpendicular, not only perpendicular to, here it is actually mentioned that E field and B field are perpendicular to the direction in which the wave is traveling. The wave is traveling. Okay, 是跟那个传播方向垂直。Okay, so here we assume that the wave is propagating to the right side for the upper graph. Here, we consider that the direction of the propagation is actually out of the page. Out of the page. Okay. This small figure doesn't really mean different location. Actually, this is like all of them are at the point P. Okay. It just tells you that at the first moment, okay, when we look from the right side, okay, to the left side, okay, look at the point P, okay, so the E field is like this, and then sometimes later, delta T later, okay, it becomes like this, and then delta T later, so on and so forth, okay. So it just tells you that the E field and B field are always perpendicular to the direction of the propagation. Okay, the propagation is pointing out of the page. Okay, so E field and B field are always on the plane, So it is perpendicular to the direction of the propagation of the wave is traveling. Okay, the second property is that the E field is always perpendicular to the magnetic field. Okay, I just mentioned that before. Okay, so E field and E field are always perpendicular to each other. And then the third one, the cross product E field and B field always give the direction in which the waves travel. Okay, so you know E cross B is actually the direction of the wave travel. Okay, so here E, okay, you use your finger pointing upward and then cross to B, your thumb pointing out of the page. So that's why I know the wave is pointing out of the page, it's propagating out of the page. Okay, so this one has the same direction. Oh, this one is 0. So okay, so this has no direction. Okay, but actually it is still propagating, but only at that moment we cannot define E field and B field. They are all 0. But actually here they are pointing to the opposite side. So actually E field pointing downward and then B field pointing to the right side. So if you cross, your thumb is still pointing out of the page. So yeah, so that means that E cross B is always the direction of the wave travel. Okay, so the fourth property is that the field always varies sinusoidally. Okay, so here we cannot observe whether it's a sinusoidal, but it tells you the conclusion. Okay, the field always varies sinusoidally. Moreover, the field varies with the same frequency and in phase with each other. Okay, so yeah, so actually it's sinusoidal and the field varies with the same frequency and phase. Okay, same frequency and phase. So you can see they are maximized at the same time, they become smaller and then become 0 at the same time, and then yeah, become maximized again at the same time. So that's why they have the same frequency. Okay, so always varies sinusoidally. So as I mentioned before, for a linear system, if you provide a sinusoidal to it, and then the output will also be a sinusoidal with the same frequency. So even if the EM wave is not sinusoidal, you can also decompose it in different frequency of the sinusoidal, or let's say maybe we have 2 frequencies, so you can consider it one by one and then you add them together. So yeah. So and as I mentioned, the linear for the linear system, yeah, if you input a sinusoidal, the frequency doesn't change. So that's why usually we will consider the sinusoidal as an input because we can apply the superposition. Okay, so here it directly tells you the solution to the wave equation before mentioning what is the wave equation. So you can try to accept it is correct. Okay, so it tells you that E equals EM. EM is the amplitude of the E field times sine of open parenthesis kx minus omega t close parenthesis. Okay, so this is the EM, the E field. Okay, EM equals E equals EM times sine of this thing. Okay, and then B equals BM. BM is the amplitude of the B field, and then times sine of the same thing. Sine of the same thing. Okay, so yeah. So you can see they are having the same phase, same frequency. Okay, this is the omega is the angular frequency, so they have the same frequency. Okay, but actually it does not like sine of omega t. We also have the kx here. Okay, so x is of course in the x direction, x direction. Okay, so we assume that this is the x axis. This is the x axis. Okay, so roughly like that. Okay, so here, of course, we know what is x. X is the x-axis coordinate. Omega is the angular frequency. Omega is the angular frequency. Omega is the angular frequency. T is the time, we know. But what is k? What is k? K is called a wave number. K is called a wave number, and the k will satisfy this property called k equals 2 pi over lambda. K equals 2 pi over lambda. Okay, which means that if the wavelength is larger, the wave number is smaller. Okay, and vice versa. So it's inversely proportional to each other. So what does it mean? What does it mean? Yeah, later when we try to write out the wave equation and try to solve it, and then you know what is k. It's probably like you try to count how many waves. Okay, it's probably like in simply like you can consider like this is lambda. Lambda is a wavelength. Lambda is a wavelength. Okay, so we can try to count how many waves are in the unit length. How many waves are in the unit length? So you can really try to count the wave number because it has a unit of a meter inverse. Okay. Yeah, so after finishing the slides of this chapter, I will tell you how we can really derive it. So up to this moment, you try to accept it is correct. And here we also have a so-called the wave speed. The wave speed, 就是波速. Okay, so the speed of the wave is omega over k. Omega over k. So you can imagine if we have let's say if we have x equals 0 and then t equals 0, then we have this part kx minus omega t to be 0, let's say. Okay, so later on it will go back to 0 because this is a sine wave. So for a sine wave, it is like going up, going down, and then going up again, back to original for a period. Okay, so let's say later on, and actually it is really propagating. So after some time, actually it is like propagating. It is like propagating in, this is the x-axis. So sometimes later, it will if it is only like this, if only a pure width, so this wave will be propagating to the right side. So sometimes later it will be something like this. Okay, so we can consider sometime later the x will become larger. So this let's say delta x over delta t. Okay, we can consider like k delta x equals or minus omega delta t, still equal to 0. Let's say we consider this point. Sometimes later it moves to somewhere else. Okay, so we try to move this part over, and then we derive k omega on both sides. So it turns out to be delta x over delta t over omega over k. Okay, so this is the wave speed. This is the wave speed. Okay, so it tells you that the speed of the wave is omega over k, and then it tells you that the speed, okay, the speed is also c equals omega over k, and then c should be a well-known constant. It is called the speed of light. C equals 1 over square root of mu naught epsilon naught. Okay, so this E naught and mu naught are the permeability and the permittivity. Permeability and permittivity. Okay, so this number is like 3 times 10 to the 8th meter per second. Okay, even for high school student, you should have remember. This is 3 times 10 to the 8th meter per second. If you really need to do some something like the modern physics or relativity, they probably will use 2.998 times 10 to the 8th meter per second. Okay, and actually if you need a more accurate number, it will be like should be something like this. Okay, if you don't believe, you can try to check it on Wikipedia. It should be something like this. 299728. Okay, it should be something like this. Yeah, so it tells you that if the EM wave are propagating in the vacuum or in the air, even in the air, the value is quite close. But if it is more correct, it means that if the EM wave is propagating in the vacuum, the speed of light should be always a constant like this. If you also learn the special relativity, the 狭义相对论, it also tells you that if it is the light, okay, if you are moving in a constant velocity to it, you will still feel like the light is moving at c towards you. Okay, even though this v is larger than 0, equal to 0, or smaller than 0, no matter as much as you are moving in a constant velocity, even towards no moving or moving backward, you will still like the light is moving at the constant c to you. Okay, so yeah, and here you see that it is the speed of light is related to these two constants, so you can really imagine the light is related to the EM. So that's why actually all the light is a type of EM wave, and of course the light we refer to the visible light. So it is only a portion of the Maxwell rainbow, but for the whole Maxwell rainbow, the speed of light, okay, we'll call it the speed of the wave speed will be c, is this constant. Okay, so finally we mentioned this one. Okay, EM and BM should have also a constant ratio, which is c, and then after finishing, I will also tell you why it is like this. Okay, so EM is the amplitude. Even for the RMS value, ERMS over BRMS should also be C. Okay, because you just take just divide them by square root of 2. Okay, so those two square root of 2 will cancel each other. So finally, it turns out to be ERMS over BRMS will still be a constant C. Okay, so let's stop here today.